All right, welcome back. Our next speaker is Aesa Kamar. Aesa is a senior software engineer at Even Financial in New York City. He's going to tell us about semilattices and how they relate to distributed data structures. Go ahead, Aesa.
Hey, what's up, guys? So I'm Aesa, and today we're going to talk a little bit about distributed data structures. We'll take a look at how we can use some cool algebra to really get a good conceptual mapping of how to understand them. A lot of the times these make up a lot of fundamentals of more complex distributed systems, things like distributed databases, distributed key value stores, and a lot more complex pieces of architecture. But we'll see if we can start simple, build up some solid intuition, and describe them with some nice vocabulary. So to start us off, let's think about a node. So a node generally is some piece of compute which has access to some memory and can do some computation. Also importantly, when we think about Unison, one affordance that we get from the Unison programming language, its runtime and a lot of the libraries, is the ability to think about locations and really talk about locations concretely within the type system. In this case, for the purposes of this talk, we'll generalize over memory, just calling it state. I'll usually use colors to represent unique concepts. So here we can see we've got a node in blue. We're imagining it happening at some location, and it's got some state. So when one of these nodes, if we want to change something about the internal state of these nodes, obviously, if a node owns that state, it's able to directly manipulate its own state. However, when we enter into a distributed environment and we have some external node or another client that's talking with our node, the only way that the internal state can be manipulated is by sending a message effectively and asking that node at that location to manipulate its own internal state on our behalf. Another important thing to consider is that this state right here to every node is locally addressable. In this case, I've just addressed them from like 1 through 9 to however many slots it's got, but it can be addressable in different ways. Like it can be addressable via a tree or something like that, or it can be a proper data structure, which is addressable differently. I'll kind of keep that abstracted and wave my hands a little bit in terms of how that gets addressed. But that's the general framing of the problem. So when we talk about going from a single node at a single location, and we want to extend this to a distributed programming environment, we've got to think about it a little bit differently. One useful way of thinking about how to make state and computations of state distributed is to think about partitioning up the state into multiple nodes and having them housed at different locations. So it's really convenient for us to take kind of some state type. Like let's say this is, imagine a 2D image, and we shard it up into different parts, and we ask a set of different nodes, possibly at the same location, possibly at locations which are near and far, to own individual pieces of that state and be responsible for, serving reads to that state and serving writes, which aim to alter, manipulate that state atomically. So then when we think about how do we actually address this state, which is now distributed, it obviously introduces some additional complexity, which is coordination. So reads and writes to distributed state require coordination from another external node, which usually is just some very simple functionality. So for example, if I'm an external client and I say, hey, get me the total picture of this happy face in this distributed system, you kind of have to ask the coordinator to go talk to each one of those nodes, grab each one of the parts of the state, and then serialize it out back to you. But in total, it's really convenient to think of this very similarly to a key value store. So this is effectively how one thinks about a distributed key value store, where we have some addressing type which is of type K, over to a total state. So this is the global state of the program, which has some type V. And what's nice about Unison is we're able to kind of talk more concretely about remote abilities and locations. We'll introduce some more concrete code a little bit later, but this is just conceptual framing of how to think about partitioned state, so partitioning up the global state and addressing it in various ways. So in order to think about more concretely one of those locations and some state that exists at a location, we want to introduce a concept that Unison provides to us to talk about that very concept. So a state of type A, which exists at a location. So there's this really cool data type that we have from the distributed package, distributed namespace, I should say, called box. And box represents something very simple. The two most important things to understand about it are this get and set operation. So get, which is just an atomic read, and set, which is an atomic write or modification operation. There's also this modify operation, which is slightly more complex, which involves a mapping function, or a function that we expect to be applied to the state that's contained within the box. But we'll really consider the important parts as being get and set. So in total, box is a really convenient way for us to model directly in Unison the concept of some encapsulated state that exists at a location, possibly several different locations. We'll get to that a little later. Okay, so we talked about partitioning one piece of state. Let's think about other ways that we can kind of distribute state. So we'll introduce the idea of a consistency group. This is kind of like a new made-up convenience term. So we've got one particular shard of our state. Let's say, for example, right here we've got this single square. We want to think about replicating that state. So when we replicate data, obviously we're bound by the fact that we can only send messages in order to affect the internal state of other nodes. So when we replicate data, we have to do it skeptically. And by skeptically, I mean that as soon as you're told new information, you don't automatically accept it into your new state. You kind of have to wait for some consensus to be reached. And consensus, there's a huge amount of research and a lot of different types of consensus algorithms, which happen in lots of different distributed systems. But the big picture of what's happening is it's all message passing, and then all of the nodes within a cluster or a consistency group go through several rounds in which they participate in message passing and voting and deciding what state to accept. So for example, this is like a really simple phased commitment where we have a single leader node which wants to accept some new state, orange square. But first, it's got to send out some messages to say, hey, all of the follower nodes, I have some new state that I want to prepare to commit. And then they send back acknowledgements to be able to commit that state. So that's cool. That seems like a nice, simple way. We've got the tools of sharding and replication to take our single node state and replicate it across multiple nodes. That's cool. That seems conceptually kind of simple. But unfortunately, this is the real world. And we have some problems that are introduced when we have message passing that happens between possibly remote locations. And also, real life is kind of chaotic. So we have, so the issues that we might encounter with these messages are that they might be passed out of order. Some messages might get lost, and some messages might be repeated. So we will, part of what we're going to try to do is address each one of these problems with a little piece of algebra, which is going to help distinctly solve each one of these classes of problems. Okay, finally some algebra. So if any of you guys are from the Scala community or have seen cats, you'll probably have seen this diagram before. We have different structures in algebra, which just represent, for a given type, what operations does this type provide for us, and what are the properties available on those operations. So the simplest that we can start with, and what's going to be really convenient for us. So this is for the purpose of thinking about the messages that we're exchanging in our distributed system. So when we get a bunch of messages, we obviously have to do, so one of the big paradigms in distributed computing is the idea of map and reduce. The reduce operation is the process of taking a lot of different messages and combining them together into a single state or evaluation, a single evaluation that our computation produces. So this combine operation is something that is really important to us. So semigroup is the simplest of structures from abstract algebra, which has the combine operation. So you can say that anything with a combine operation, so any type A, which has a function from A and A to A that's associative, can be considered a semigroup. So if you remember, we had those three problems. The problems were messages being passed out of order, messages being lost, and messages being redundant, like they get sent over and over again. So as we kind of move through this diagram, we see different structures which have additional properties that we might want out of this combine operation. So the intuition that we want to arrive at is to understand why this type is important, why this type in this structure from abstract algebra, the Semilattice, is so important for building distributed systems, and why we spend so much time thinking about it, and how it makes thinking about distributed systems easier for us. So a semilattice is a semigroup. All semilattices are semigroups. The special things that that distinguish a semilattice from a semigroup are that we introduce an additional property that we require, which is that the combine operation must be idempotent and the combine operation must be commutative. So with idempotency, we satisfy, hey, we can handle a bunch of messages that get repeated. So if I have 5 or 10 copies of a message, like let's say it gets sent because it hasn't received acknowledgement because there's some weird error that's happening somewhere in the pipes of the internet, and it just gets sent multiple times. We can deal with that if our messages form a semilattice. And then also if there are timing issues, like let's say, for example, it gets sent 5 times and then somehow they get scrambled within the network and they are received by the receiving application or the receiving node out of order, we want to be able to process those in whatever order and get back the same final state. Is a really useful way to reason about our message types. There's also one additional thing which might be kind of nice but is optional, which gets us to the monoid structure from abstract algebra, which just introduces one additional function called empty, which is just a vacuous message. So we should be able to send messages which are empty, and I can send infinitely many empty messages and just get back the same final state. It's an identity operation that does not affect the state of my distributed system. Okay, and I put groups and commutative groups on here, but they're really not important for us. Okay, so let's get some more intuition for what semilattices and semigroups and monoids do, kind of some real life examples, and why guaranteeing idempotency is actually really difficult. I love this image. There's a new project from OpenAI called DALL-E. So this is one of the images that it generated. It's an oil painting of a hamster drinking tea outside. So in this example, we can see that we can separate it out into 3 different image channels, and we consider those image channels as obeying kind of the laws of a semigroup or a monoid. So they have this like transparency channel that I can introduce, which adds no additional information. So I can add as many transparency layers as I want, and it doesn't change the state of this total system. And they have this combine function in which I can take multiple different parts of this and combine them together to get a total summation data structure, or I can get a final result, which is the combination of all of my original messages. Great. So this is nice. It's easy for us to understand how this is associative, how this is commutative, but in a lot of real-world situations, guaranteeing idempotency, and I guess also commutativity, are a lot harder to guarantee. And we'll see an example why. So for example, if we had this green channel, so a message with the green channel coming into our distributed system, and we accidentally accepted it twice, then this does change the final state of our program. So of our distributed system state, I should say. So there are a lot of situations where things can behave as proper monoids, but don't behave as semilattices, which make it really tricky for us to distribute. So this is a really useful structure that gets introduced when we enter the territory of thinking about distributed systems. It's a thing called a vector clock. So just to kind of understand this picture of what we're looking at. So this is a timeline here, and we're going to kind of visualize the evolution of message delivery between three nodes in this small distributed system. So when I say vector clock here, that sounds kind of complicated. I know when I first saw that term, I was like, oh, that sounds imposing and kind of scary. But all it means is that, so the word vector itself just means like an array of fixed size. In this case, the big idea is that we're keeping track of all of the timestamps. So the last seen event timestamp for each one of our nodes, we're just keeping track of that. And we're going to tattle or gossip that information out to the rest of our nodes whenever we get new messages or send new messages. I'm going to play this animation here. It's going to be kind of complex, and then we'll go back and we'll analyze what's happening here at every step in time. So we see from time 0 that somehow this is our leader node up here. So it gets informed, probably by an external system, that its state is changed to 2 dots. So in order to commit that operation while it's running its consensus algorithm, again, this is a very simplified consensus algorithm, so please bear with me. So we see the timing of the global vector clock incrementing up as we scroll through time. So at time 0, it's somehow notified that it got this state 2, and it sends out a request to prepare, hey, I've got the state 2, and broadcast that information out to the rest of the nodes in that consistency group. So the message gets received. In this case, this example is a little bit unrealistic because we're assuming immediate acknowledgement. So this little dashed line here at time 2 is just node 2 is acknowledging to node 1 that, yes, I've received it and I acknowledged your preparation and it's okay to commit. But the second message that gets sent out somehow gets delayed through the network and only arrives at time 4. Okay, that seems kind of simple. That makes sense. So we'll look also at, so I know it's a little bit hard to see here, but this representation right here is the last known state of the vector clock as reported by the sender of that message. So at time 1 here, node 1 sets the vector clock in that message to be, hey, me at node 1, I know that I'm at time 1, but the last known states that I've seen from nodes 2 and 3 are 0 because I haven't gotten any new messages from them or any new acknowledgements. Cool, that kind of makes sense, but doesn't seem very useful. So the useful intuition that we have here is that vector clocks have the ability to form semi-lattices when you consider time ordering and this fold operation of wanting to fold new messages into its internal state. It behaves sort of like a semi-lattice, which is really nice. So the observation is that this is going to provide us with a combine operation, which is associative, idempotent, and commutative. So let's run through a slightly more complicated animation here. So at time 0, we've got our leader node is informed that its state changed. and we have the same operation happening where it sets the vector clock to be 100 on those messages, and it sends the request to prepare those messages out to its two follower nodes. But then at time 2, somehow its internal state is then again updated to state 3, and it prepares a new state update message at time 2. So we'll see kind of interestingly here that at time 2, it knows that its vector clock is at time 2, but it also would have received an acknowledgement from node 2 that node 2 received a message. So it knows that the second node has a vector timestamp of 2. So its timestamp is a 2 because it got the acknowledgement. So it's able to send a message with a higher timestamp than the first message that it sent out. So in terms of reception, node 3 says, oh, okay, at timestamp 3, I received this message, which appears to be newer than this message. And I know that it's newer because I've seen a later timestamp. So this kind of guarantees that we can get these vector clock messages, which are sent out, which can be commutative because it knows how to resolve the partial ordering of when those messages must have been sent. So it's just relative ordering, not total ordering, because obviously things can happen seemingly concurrently. So it knows that like certain events had to have happened at least before or at the same time as another event. Cool. So let's introduce another unison type, which allows us to implement kind of this vector clock arithmetic, and which is really useful as a building block for building distributed systems. So there's this also in the distributed namespace. There's a nice type that we get called dvar. Ooh, this is interesting. If I open up the API for it, I see it's got these two functions here. One's called meet and one's called join. That's kind of named weirdly, but the implementation of this is pretty much, take these two timestamped A types, right? So these timestamped A messages, decide which one's the latest, and decide whether or not I should accept this new state if I should accept this new message state. So thinking about why we see those names, meet and join, this kind of comes from a long history of mathematics, of studying these things. A lot of the time, it's a lot of people ask, like, why do we use a lot of these kind of archaic names? Like, why do we call it semilattice? Why can't we just call it combinable? That would be so much easier and make so much sense for people. But the real reason why we keep names is because we get a really, really rich history of a lot of mathematics, a lot of research, a lot of proofs that we can rely on. So in kind of the literature, the way that semilattices are defined, they have these operations called either meet or join. And obviously, this is the literal Wikipedia page for semilattice. And the operations are usually called meet and join. So that's just an explanation about why we see in dvar that although I told you the requirements for semilattice were just the combine operation with properties, a lot of the time you're going to see semilattices which actually call things as meet and join as an operation. Okay, so kind of zooming back out to the understanding of our intuition of a distributed system. So this is one single shard of our distributed system with a consistency group where it's kind of gossiping a lot of these messages or getting total consensus about the acceptance of new messages that change the state of our system. And then we've got the way that messages get passed around and the structure of these messages. They have vector clock timestamps attached to them, and they talk about, hey, here is the state updates that we're trying to run. So a lot of the times, if you look at the literature, this is the first time I'm going to mention the word CRDT. So a CRDT is a conflict-free replicated data type. So it's replicated, and by conflict-free, we mean that we can guarantee that even if we have messages which are, we can guarantee idempotency, commutativity, and associativity, as all that really says for us. It's a semilattice. So there are two kind of flavors of CRDTs. There are operational transform CRDTs, and there are state-based diff CRDTs. So we can either, so within these messages, right, we can either send, here's the local function that I applied in order to change my state, and please acknowledge that you've received these transform messages. So for example, like in Google Docs or something, if you need to share edits, you just send the diffs, your state diffs, as a simple update operation. Or if I have a distributed counter, I just say I incremented my counter by 5, rather than saying, hey, my new state is 42. So two flavors of CRDTs that are implementable. And we've seen also how it's really convenient in Unison maybe to express this concept of a vector clock message using dvar, and the idea of a location-bound computation with an atomic commit operation, this atomic modify and set operation, and a get operation as box. So those are kind of two nice building blocks that we can use. And in fact, there's a lot of really good stuff in that distributed namespace, which are good building blocks for building distributed systems. Okay, and extending that picture up a little bit. So this is one consistency group that we've got right now. And we can, we talked about the ability to take this state and have it be partitioned up into multiple partitions of that state, multiple shards. And each one of those shards, we can have a single consistency group, which is responsible for ensuring consistency of that particular shard. And this is nice because each one of these consistency groups can respond independently, can respond elastically. So I can have some really hot part of our state, which gets read a lot, and I'm able to kind of smartly design APIs, which are able to coordinate activity, which can talk to each one of these shard sets in my, or each one of these consistency groups, which is responsible for a single shard in my distributed data system. And I can be like, okay, I don't care as much about having strong consistency. Like I don't need to necessarily be able to read back the same value that I just read. I just want to grab whatever's in the latest register from whichever one of these nodes and just have really, really high read availability and like read latency out of the system. And it's nice because we are afforded the ability, because we're afforded the ability to think about these distributed systems as being responsible for just a single piece of the state, right? Because in Unison, when we talk about, we can talk about entire distributed elastic computations as values rather than talking about them as servers. That gives us a new expressiveness with which we can talk about the APIs that we design to mutate values in a distributed system and to read values in a distributed system. So hopefully we can build a lot more expressive tools to be able to, because we can think about them in like a more, we have better concrete types to be able to express distributed computations. We can also make better functions and APIs to be able to interact with a lot of those distributed systems. Let's see. Okay, so one other piece that we haven't really talked about. So we've talked about message passing and we've talked about state a lot, but there's one really important piece into understanding how that message passing actually works. We didn't talk a lot about distributed consensus algorithms. And I guess for the purposes of this talk, Distributed consensus algorithms there's a whole lot to read, and they're kind of complicated, so we'll kind of elide over that for now. Two of the big flavors are Paxos and Raft. Those are ones that you're going to see a lot in the literature, and I've been trying to learn about them a lot. But in abstract, we know that we want the messages that are exchanged, so the state messages, we want them to behave sort of like a semilattice, because we want them to have the properties of associativity, idempotency, and commutativity. But generally, the way to think about them is that it's a bunch of nodes coordinating their activity, and they split up this consensus problem into multiple phases and pass along messages of like what acknowledgement state that they're in. And that's generally how, if you squint and look at all consensus algorithms, that's more or less what they do. Obviously, they're very specific, and there's a lot that you have to do in order to prove the correctness of a distributed consensus algorithm. That's why we have a lot of great tools like TLA Plus, and a ton of research and a lot of code review goes on to build these things. But if you squint, that's generally how to look at things. Okay, and a final reminder of why exactly we're doing all of this again. Why are semilattices even a useful thing to think about when we're building distributed systems? So as we know, in distributed systems, we're kind of at the mercy of this cap theorem. So we've either got to choose consistency, we've got to choose availability, we've got to choose partition tolerance. We can't have them all. Distributed systems also behave really chaotically and wildly. They have the potential to behave really chaotically, just because the amount of possible states that a distributed system can be in is so much higher than the amount of states that a traditional single node computation can be in, because of the network architecture. There are so many permutations of message delivery, of message failure, node failure states that the system can be in, that the computations just get necessarily so much more complex. And because they're complex, we need good conceptual tools to be able to wrangle down that complexity. And a lot of the times it's really useful for us to borrow structures from abstract algebra to put nice conceptual bounds and be like, we know this, we've proved some properties about this mathematically, and we know that we can abstract over them generically and build really powerful machinery without having to rebuild a lot of our proofs of that our intuitions are working a lot of the time. So that's why it's useful. Hopefully you guys have a better intuition for how to think about why semilattices are useful and how to build really robust message delivery systems, and just be like, oh, I just got to match the semilattice interface, make some tests for that, and have a nice, simpler kind of foundation for how to write a lot of these correctness tests. Cool. I think that's my last slide. That's all I got.